that we're very happy to have Severin Lüst here telling us about how to computationally attack tadpole problems. So take it away, Severin.
Okay, yeah, thank you very much. Thank you very much also to John and Cody for setting up these very nice seminars and for giving me the chance to speak here. So today I'd like to talk about this paper, which has, I believe, the same title as my talk, which we finally put on the archive a couple of weeks ago, which is in collaboration with Joseph Boehner, Johan Blab, and Mariana Grania. So as you know, when studying flux compactifications in string theory, we expect to have a huge number of possible flux configurations. Therefore, a huge landscape of string theory vacua, which is estimated to be the size of 10 to the very big number possible vacua. There's estimates like something like 10 to the 500, and F theory even more. And the larger, obviously, the Hodge number of a Calabi-Yau manifold, the larger the number of cycles is, the more choices I have for fluxes. However, these fluxes are not completely arbitrary. They have to satisfy certain constraints, namely, or most importantly, they have to be integer quantized, and they can also not be arbitrarily large. Their size is constrained by so-called Tadpole cancellation conditions. And these two constraints together, they put rather stringent constraints onto these fluxes, which are admissible. And therefore, it's a very natural question to ask, which are the physical properties of the consistent vacua which satisfy all these constraints? Do they have physically desirable properties? So to study the landscape of flux, vacua, and string theory, one could possibly imagine many different approaches. For example, the most straightforward one is a systematic approach where I try to extensively scan, or at least randomly enumerate a large number of flux vacua to get some statistics. And that way, maybe even for very special examples, try to list all possible flux vacua. But typically this approach is very difficult because there's just too many vacua normally. That's not feasible only for very specific examples, for example, where we have a small number of moduli. This, for example, this very nice paper which tried this approach for some toroidal orbifolds. On the other hand, I can try to use some statistical approach, try to estimate the number of flux vacua by some statistical methods, as for example done in these well-known problems. However, probably the most desirable way to attacking this problem is this analytically, by exploring the mathematical structures and some symmetries beyond that, and to actually get some nice, strong formal results. And I think for most of us, this is kind of the most desirable thing to do. Very closely related, which kind of taking a little bit of an orthogonal but related approach is Swampland program, but I don't want to say too much about it now. And recently there was another possibility to study the landscape, namely algorithmically, by using modern big data, artificial intelligence, or machine learning algorithms, which is the path I would like to take today. So machine learning or artificial intelligence recently, I think, as all of you are aware of, attracted a lot of activity for string theory related problems. I cannot list all relevant papers here. For an overview, there's, for example, this very nice review by Fabian Rühle. And so the strategy I would like to talk about today is to use certain algorithms which are inspired by biological evolution or genetics, and therefore also called evolutionary or genetic algorithms, to search or to generate specific vacua, string vacua with very specific vacua, and to look if we can find desired vacua in the string landscape. Again, there was previous attempts going in a similar direction. I probably forgot some papers, and I apologize for that. And the idea here we want to focus in is to specifically search for flux configurations where, for example, all moduli are stabilized, and we want to see how generic are these in the string theory landscape. Are they hard or are they easy to find? So for that reason, let me very briefly review the problem of flux compactification here for the example of F theory or M theory on Calabi-Yau fourfolds. Usually we have a kinetic term for the four-form gauge fields, and since the Hodge star here depends on the Calabi-Yau metric, this generates a potential for the moduli, gives masses to the moduli and stabilize them. One can also use a superpotential formulation, and then the modular stabilization essentially reduces to some F-term equations. For example, if I reduce that to the complex structure sector here, this should actually be H31 for a threefold. Then I have exactly the right number of equations for the right number of moduli. So generically, I would expect that I'm able to stabilize all of them. However, working out this approach is in reality, that's kind of complicated, because I need to know these period maps. I need to know these period integrals, which are generically solutions of very difficult equations. On the other hand, these fluxes, as I said, they have to satisfy certain constraints, namely the Tadpole cancellation constraint. And in F theory or M theory on Calabi-Yau 4 language, it is written in this form. On the left-hand side, I have the integral over the fluxes. On the right-hand side, I have the Euler number of the fourfold divided by 24. So I think a natural question to ask is, how does this constraint scale in the limit of large H31 of a large number of complex structure moduli? And for the Euler number, this is actually pretty easy to figure out. We just have to look how to express the Euler number in terms of the Hodge numbers. And then if H31 is the leading contribution, then this is just proportional to 1/4 of H31, the number of complex structure moduli. So it is natural to ask if we have a similar linear scaling behavior for the charge coming from the fluxes, the integral over G wedge G. And of course, this question is much more difficult to answer. However, in a recent paper, we conjectured that we still have a linear scaling relation here, demanding that we are able to stabilize all moduli with fluxes with some proportionality constant. And then, of course, the big question is how large is this proportionality constant? Is it larger or smaller than 1/4? Then we would get very different qualitative behavior. And very interestingly, we looked at a few examples in the literature where this is worked out explicitly. And all of these examples are more or less compatible with alpha being approximately 0.4, which, if true, would be very interesting, because 0.4 is actually larger than 1/4. So we would not expect to be able a large number of moduli. So we would like to get a bit more evidence for this behavior and see if we try to specifically solve for flux compactification with as small charge as possible. Do we still see a behavior like this? And for this problem, I think using big data or artificial intelligence algorithms is a very natural approach. So we try to use these algorithms to systematically search for flux configurations which A, stabilize all moduli, B, at a as generic point in moduli space as possible, and C, with an as small charge as possible, to see if we can find evidence for this behavior. And for that, we used algorithm which is typically called differential evolution. So how does such an algorithm work like? It's a global optimization algorithm, as I said before, inspired by biological evolution or genetics. And the goal is to find the global minimum of a certain fitness function, which is a function which maps some vector space R to the n to R, and the value of this fitness function is just telling us how fit a sample solution is, and we would like to find the fittest one. And the nice thing about these kind of algorithms is that we do not need to know the gradient of this fitness function. So we do not descend the gradient of a function, but we kind of use maybe more clever strategy. So the idea is to set up a population of n, possibly a large number n of sample solutions, which we at the beginning populate randomly. And then we take this population and we let the individual elements of this population reproduce and mutate by randomly combining and changing elements. I'm skipping over all of the details here. Of course, in the end, it matters how exactly we are doing that, how are we selecting elements for doing these operations and so on. But just to get like the big picture there. And then after we did that, we created a lot of new elements. And then we select the fittest elements with a minimal f. So we obtain a new population, which probably is a bit closer to our goal. And then we repeat this process iteratively until we either find or sufficiently approximated the global minimum of this function. So to apply this to our problem, the challenge will be to design a suitable fitness function of this kind. However, if I would use this approach as I indicated earlier, by solving F-term equations, I would still need to know what are these superpotentials. I would still need to know these period integrals. So this would still be a very difficult problem. So for that reason, we looked at a very specific example, namely K3 times K3, which you could most understand like as a universal playground for flux compactifications, because things are a bit easier here. Again, there's a broad literature on this subject, and I only mentioned these two papers here, but there's certainly more. In particular, this very nice paper here by these people, which showed us that we can actually stabilize all moduli, the scalar and complex structure moduli of this space due to this hyperkähler structure of K3 times K3. And in particular, there's no knowledge of complicated period maps necessary. Everything is kind of easy and can be done by studying integer matrices actually. So, and to actually make this even a bit more general, we decided not to study K3 times K3 directly, but to study or to solve a closely related general lattice problem. So here's the problem we are trying to attack by this algorithm. So we start with an even integer lattice with so far general arbitrary dimension, and we need to specify an inner product on this lattice specified by integer matrix, which I think in mathematics terms is called the Gram matrix. And then we want to find integer matrices which sit in like this tensor product. So these are for us, they're just integer matrices. And these integer matrices together with this integer, with this inner product, they can be translated into these two combinations of matrices. So G, D, G transpose D, and also this combination. So we get another integer or another pair of integer matrices. And now we study the eigenvalues and eigenvectors in the spectrum of these matrices. And we want to put the following constraint on these matrices G. We want that these matrices are diagonalizable and that all eigenvalues are actually non-negative. So they have to be real and non-negative. Moreover, we want if one of the eigenvalues is degenerate, we want that this inner product on this eigenspace has a definite signature. And we want that there's no root, so no vector of norm 2 of this lattice is orthogonal to the eigenvectors of positive norm, kind of depicted in this figure here. So we do not want this situation to happen. So these are very specific requirements which are kind of easy to put on the computer. And moreover, we want to minimize this quantity. We want to minimize the trace of these matrices. So we want to find matrices, integer matrices G, which satisfy all these constraints and where this combination is as small as possible. So how is that related to physics? This was shown in this very nice paper here. And in particular, this is exactly related to flux stabilization, flux compactification, modular stabilization on K3 times K3. If we choose a very specific lattice, namely the lattice corresponding to the middle cohomology of K3 the K3 lattice, which corresponds to 2 copies of E8 and 3 copies of this so-called hyperbolic plane. So, and then we can translate these conditions into physical condition. The first condition of having non-negative eigenvalues guarantees us to have a Minkowski vacuum. The second condition guarantees us that all moduli are stabilized. And the third condition of having no roots of this lattice orthogonal to norm eigenvectors guarantees us that the K3 manifold, that these 2 K3s are smooth, because actually these roots, which correspond to orbifold singularities of the K3, and these roots, if they were there, if they were orthogonal to the spaces spanned by the positive norm eigenvectors, they would correspond to the gauge group localized at these singularities. But let me not go into the details here. And moreover, finally, the flux charge to the integral G, which G is just given by this trace, which we want to minimize. So we are now in a very good position to put this onto a computer. So we now have a good idea how to design a fitness function. So to operate with these optimization algorithms, the first problem we encounter is that they usually better operate on a real input space and not on an integer space. So the first step we do is we just simply round to the closest integers, and then we compute the spectrum, the eigenvectors, and all these kind of things we need to know about these matrices for these 3 conditions, 1 to 3. And whenever one of these condition is violated, we assign a certain penalty to it. For example, if we have a negative eigenvalue, this penalty would, for example, correspond to the absolute value of this negative eigenvector. And we finally also need to compute this trace. And the fitness function in this case will then be the weighted sum of these penalties and of this charge. So by minimizing this fitness function, we try to set all of these penalties equal to 0, and we try to find the as small charge as possible. So this fitness function tries to do exactly what we want. So next to implementing these penalties, the difficulty is to determine these weights in such a way that we achieve this problem, this solution, as effective as possible. So we did not implement this algorithm ourselves. We used existing implementation in the Julia programming language, and we encountered a few challenges. The first challenge is that the search space is actually really large. It's a huge search space. And the second problem is that this finding roots orthogonal to eigenvectors, it's in itself an NP-hard problem. One could probably talk a lot just about this problem. So altogether, this thing converged rather slow, and we used an additional local search around the minima, which we found, which we call the spider algorithm. But I do not want to talk about this now. So altogether, we see that this still works very nicely, but it works particularly nice for smaller lattices where we actually see very fast convergence behavior. So let me illustrate this with 2 examples. The first example is this 6-dimensional lattice, which is just 6 copies of this hyperbolic plane, where for you, this Gram matrix is just of this form. So this has actually signature 3,3. And we set up, for example, here, what I show here, we set up 8 populations, which each have 500 elements. And then you can see how the charge Q is distributed in these populations here after 60 seconds, 2 minutes, 5 minutes, and 30 minutes. And one sees that in the beginning, after 60 seconds, one still has like a nice smooth distribution somehow, where Q is localized around 12 or something. However, after half an hour, almost all Q are accumulated have the value 5, and there's just a few left with 6. So the population become much more uniform. So we assume that we actually found a minimum, that the population converged against a global minimum of this fitness function, and that actually the minimum of Q is 5. So we could run this even longer for many hours, and we would only find matrices where Q is 5 and never one where Q is 4. So in this case, we would conclude that this minimum Q here is 5. We could do the same thing for larger lattice, for example, E8 times E8 times one of these use factors. And here the dimension would be 18. And suddenly the problem is much harder. We see that we still have a convergent behavior towards smaller values of this Q. But this, for example, the last snapshot is after 36 hours. But even after 36 hours, we are not sure if we really converged against the minimum or not. Notice that here also the populations are larger. So we did this same game for a large number of lattices, actually, which are depicted here in this table. The green ones are the examples I just showed to you. And the red one is the one we are actually interested in. This is K3 times K3. And I think there's one observation we can clearly do, that this minimal Q we find is always roughly of the order of the dimension of these lattices, which I think becomes very clear from this analysis. So let me say a few words on the interpretation of these results. So for small lattices, we see a very quick and reliable convergence behavior against the Q of order of the dimension of the lattice, and this really seems to be universal behavior. More difficult thing to answer is what is the actual value of this Q, in particular for larger lattices, and in particular also for the K3 lattice, which has dimension 22. So the problem here is, assuming that we found a putative Q minimal, we want to know what is the probability that the absence of any Q larger than this minimal Q is just a statistical effect. So in other words, did we create enough statistics to be sure that we are not just missing something because we did not try hard enough? And to really answer this question, one would need some knowledge of the distribution of these Q and the quantitative performance of the search algorithm, which is something which is very difficult to have because this is actually what we are after. We want to know how are these charges distributed. So let me also illustrate quickly what we found for K3. So here we actually found a huge number, roughly 10 to the 5 matrices where this minimal Q is 25, but we do not find any matrices where Q is 24 or smaller. And I would like you to remember that the bound by Tadpole cancellation is actually 24. Of course, here again, you could ask, is this just a statistical effect? Why are you sure that this is the right answer? But however, so we tried this a lot of times. We let this algorithm run for actually weeks, and we easily generated this large number of matrices with a tadpole charge of 24, but we never found anything smaller. So by now we are very confident that this is actually the best we can do. So this indicates that the modular stabilization at the generic smooth point in modular space is not possible within the tadpole bound. Moreover, we can compute again this proportionality constant in this Tadpole conjecture by dividing this minimal Q by the number of moduli. And if you divide 25 by 57, you should get something which is roughly 0.44, which agrees very nicely with the numbers we found in the literature. So we see this as further very strong evidence for this linear scaling behavior. So what is the upshot from that? So for this example, M theory on K3 times K3, we see that apparently we cannot have all of these three properties when satisfying the Tadpole cancellation condition. We cannot stabilize all moduli at a generic point in moduli space with an orbifold singularity, with fluxes which have an arbitrary small M2 charge, in this case Q smaller than 24. So this means fluxes with a small charge always come with additional light degrees of freedoms. So it appears that flux compactifications are are not as generic as one thought. One cannot just start with a generic flux vector and get everything you want. So thank you very much.
Great. Thanks, Severin, for the very nice talk. If anyone has a question, please type "I have a question" in the chat, and I'll get to you. Let us thank Severin with our clap emojis. While we wait for questions, I have, I guess, two. The first is, you said that these differential evolution algorithms didn't need any gradient information. So I would have thought that the conversion into reals for these problems, one of the benefits of that was the ability to take derivatives and the ability to, kind of do gradient descent. Why can't one do something like a integer valued, purely integer valued updating scheme?
I think we experimented a little bit with that, and it performs actually vastly inferior to working over the reals and rounding them, because internally I think this algorithm is trying to approach the minima by doing small steps, by like having some real valued vector and then just tuning it a little bit, and combining real vectors, and so taking real vectors, combining them into a new real vector and rounding to integers generically gives a different result than taking two integer vectors, combining them. So doing the rounding first and then the evolutionary algorithm steps, or doing these evolutionary algorithm step first and rounding them gives different results, and actually working with the reals seems to give better results.
Okay, and I'll leverage my power as moderator to ask another question. In your population graphs with time, it seemed like you were only culling participants, or the total number of things that you were keeping track of was shrinking over time.
So there's two things. So these populations, they stay at the same size. So in this case, 8 times 500. But I'm only showing those which satisfy these three constraints. So where these penalties are 0, so which I would consider like good flux compactification. The only thing we don't satisfy is Tadpole cancellation. And then I only show unique solutions. So you really see that the population seems to converge to something, and that actually the diversity in this population dramatically goes down. I mean, we only have like order 50 different matrices left. So it really strongly seems to converge to something.
I see. That makes sense. Jim, I think it's next.
Hey, Severin, great talk. Always good to hear a talk instead of reading the paper, because I feel like I understand it better when you present it. Quick question. So at the end, you sort of have these 3 conclusions, sort of not all 3 of these can be true, takeaway. And it seems that the takeaway that you guys are sort of proposing is that in this context, in this particular example, it suggests that we should be trapped at enhanced symmetry points, which is, similar to what we see in the real world. My question is regarding the extent to which you think this conclusion might apply more generally, because something that's interesting is that when you sample known F-theory geometries, for instance, from a uniform distribution on known F-theory geometries, overwhelmingly at generic points in moduli space, there is symmetry. So could you maybe comment if do you have any expectation of what you expect to be true as you branch out to broader examples that have these properties?
So yeah, the short answer is I don't really know. I think the lesson we learn here is that we are drawn to like non-generic, to special points in moduli space, and for K3 times K3 we can really make like a one-to-one correspondence between these special points in moduli space and points with enhanced symmetry. For F theory, as you see, for like more generic Calabi-Yau one might even see some singularities, even as generic points in modular space as possible. So I do not want to say that we cannot have singularities, we cannot have light gauge groups, but what we seem to see is that things become more difficult the more generic the point in modular space is we are looking at.
Yeah, maybe the sharpening of my question that you just introduced, sort of based on this example, is it that you expect to be trapped at non-generic points in moduli space, or that you expect to be trapped at points at which you have additional light degrees of freedom? Because these are sort of two separate things as you vary the examples.
So a priori, I would probably say the first thing, I would expect to be trapped at special points in modular space. And I don't really know what special in a concrete example always needs. But in this case, 3 times K3 example, special clearly seems to mean having an orbifold singularity, having a gauge group.
Thank you.
But it would be interesting to see what this means for like honest Calabi-Yau fourfolds.
Great. Andrew has already anticipated me calling upon him.
Thanks for the talk, Severin. So, well, just a more technical thing about the algorithm. You had this fitness function with different weights there, and you said something that you fixed the weights experimentally. I didn't quite get what you meant there. So could you comment a bit more on that?
So we have these weights, and these weights kind of determine how important the algorithm considered one of these penalties. And for example, what it tries to. So if we have these 3 constraints, and we could, for example, put a very high constraint on very high weight on one of them. And this would mean that the algorithm tries very hardly, to solve this penalty very quickly. So it really tries to push this penalty towards to 0, but it could, for example, still allow for the other penalties where we have a slower weight for them still to have a small non-vanishing value. So the name of the game is somehow to find these weights in such a way that we really converge nicely and evenly to what we want to converge, and that we do not try to oversolve one of these constraints by completely neglecting the other one, like to find a good middle ground. And since some of these constraints are more difficult to solve than the others, one has to play a little bit around with these weights to find something which actually works well in practice. But we don't really have a systematic way of doing so. We just started and we took different values and we saw what works best. And so on.
It was more trial and error. And,
yeah, this is kind of what I mean exactly.
All right, thank you.
And finally, Jakob.
Hi, thanks for the nice talk.
Hi.
Let me maybe latch on to Jim's question. I didn't quite understand. Are you suggesting or conjecturing that modular stabilization at special points with, say, enhanced symmetry is universal, or it's just sort of more generic than one would have thought, or what is the statement?
So it's very difficult, I think, to make a general statement about general fourfolds. But so in this example, we clearly saw that we can only get modular stabilization, complete modular stabilization, if we are at a special point in modular space. If we had as generic point as possible, then we could not stabilize all moduli. So what I would conclude, if I can extrapolate this to other fourfolds, is that it is more easy to stabilize all moduli at some special points in modular space than in like the generic bulk of modular space.
Yeah.
So we are kind of attracted to special points.
Yeah, I know I'm sympathetic to the idea that you're attracted to special points. It's just, I mean, this example is extremely special, right? It has.
I agree with that.
You're breaking supersymmetry from 2 to 1 or 0 by introducing fluxes versus breaking from 1 to 0. Which, I mean, have you thought about whether there's some SUSY argument why this had to be true for this particular example?
No, I don't have a very good argument along these lines. No, unfortunately not. I would be very happy to learn about that.
Yeah. Okay, thanks.
Thank you.
Great. With that, let us thank Severin again for his excellent